Hi, welcome back to the Calculus 3 problem solving sections. This is the second part. For the first part, we did three kind of practice problem, how to solve the line integral by using the Green Theory. So today, let's continue here. All right. So in here we have the number 2. We said use the Green Theory to evaluate this integrations here. All right. So the first thing is here, we know this is my pxy. So let's always write that pxy equal x to the 2/3. All right. So pxy is x to the 2/3 plus y squared, and the qxy is equal to y to the 4/3 minus x squared. Okay, so now the first thing is let's do rho p rho y. So this will be what? Rho p rho y will be 2y's, right? All right, so will be the 2y's. Okay, and then the rho q rho x will be what? Will be the negative 2x's here. Obviously, this is not equal, so it's not the conservative field. So, okay, so now the only things here we need to be careful here. So this integration here, right? So this integration along this curve, okay, x 2/3 plus y squared dx plus y 4/3 minus x squared dy here. So be very careful here because this curve go this way, right? So it's clockwise. So we know the green theory is working if my curve is counterclockwise, it's a positive orientation, and this one is a negative orientation here. So now I will just reverse it. So I will say, okay, so how about I put the backward c here, right? So this is x 2/3 plus y squared dx, then plus the y the 4/3 minus x squared dy here. Because I put the reverse, so I need to put a negative sign here. All right, so be very careful. I need to put a negative sign here. The reason why is because I changed the negative orientation to a positive orientation by put a negative sign, reverse the curves here. Okay, now this one's here, all right? So now this things here can be written, this negative sign still there. So now this after I made the change, right? So now this negative C become positive orientations and the closed curve, right? So I can apply the green theory. All right, so the green theory, so let's see here. So it's rho q rho x minus rho p rho y. So it's rho q rho x is minus 2x, all right, minus 2y. Okay, now over this area, this is my D areas, right? Then the what? dA. Okay, so now let's take a look. How do I integrate that? Okay, so here, now I can do this. Okay, so it depends, right? So if you want to, so this negative become positive. So I have 2x plus 2y. So it depends, you want to integrate the x first or you want to integrate y first, right? So now I said, let's do the x first. Okay, so this is a dx here. So remember, right, when we did integrate from the x first, that means I'm starting these directions, right? So go here, go here, go here, right? So if you do the dx, right? So x equal to the y square. So I start at y square. Now where I end here, I end at the 4th, right? Okay, so after you finish that, then where is your dy's here? So the y, so you can see the y functions here, so the dy's, right? So y is from where to where? From the 0 to 2. So this integration become a pretty easy integration here. All right, so here now you can just do like what we did. So this is 0, 2, and then this will just be x squared plus 2xy. Then you input upper bound minus lower bound, right? Then you take a look at the dy afterward. So after you substitute the upper bound minus lower bound, then this one will be the 16 plus the ay and minus y fourth and minus 2y cube dy. Then this one is pretty easy, just the power rule all the way down, substitute to the numbers, and I will get my answers here will be 168 over 5. So that will be the integration for this line integrals here. All right, so it's pretty, so for the green theory, this is pretty easy. All right, so let's do one more. All right, so this is the, okay. So the number 3, let's say a particle starts at the origin, okay, and move along the x-axis to the 5, 0, then along a quarter circle, x squared plus y squared to the point 0, 5, then down to the y-axis here. Let's see. Okay, so this is what is the, okay, so it's 5, 5. All right. So let's say I have this. Okay. So this is my my curve. It started at 5, 0. So it started here. Okay. Started at origin. Okay. Started at origin. Move to the 5, 0. Then along the semicircles here. So oh, excuse my circle doesn't look like a circle. All right, but here it's smooth here, right? So from my circle, then I travel. Okay, so from my circle, then I travel to the 0, 5, then going back down here. All right, back down to the 0, 0. So I want to find the work done on the particle. Like we did on the the video number 1, if you want, you can always, so define that this is a C1, this is a C2, and this is a C3. So you can do 3 sets of the, you can do 3 sets of the, the parametric function and substitute back in here. Okay. All right. So now this is f of xy. This is my field here. Okay. So I know the work done is equal to I am, the integrate along this curve, then is the f, right? So it's this field dot product d r's here. Okay. And so in here, right? So let's try to write my pxy again and the qxy. Okay, so pxy is sine x, qxy is sine y plus xy squared plus 1/3 x cubed. All right, so let's see the rho p, rho y. Whoa, what is rho p, rho y? Whoa, it's 0. Okay, that's easy. Then rho q, rho x here. Rho q, rho x will be y squared plus x squared. Hey, that's easy. Okay, so now I can change this one. Okay, so I can change this one to the traditional integration over these regions, right? This will be my regions here. This is my D. Okay, so this will be my D. And then I'm going to have x squared plus y squared. And so it's a rho q rho x minus rho p rho y. All right, then I have a dA here. Okay, and okay, so now let's take a look here. This one's here. Okay, so this is the one we said, how we do that? Okay, so this is what I want to integrate, right? So I can say x equal to what? I can use the polar system, the r cosine theta, and the y equal to the r sine theta. So correct? And so in here, this one will become 2. So I change it to the polar. It's easy to manipulate. So remember, so x squared plus y squared, this is equal to the r squared. Now remember the polar, this is the polar coordinates, right? So what is the Jacobians here? Jacobians here is r. Okay, so now I can times the r and then the dr d theta. All right, because this is the quarter circle. So what is my so what is my r's here? R is from where to where? 0 to 5, right? And then my angle theta here. Theta is a quarter of the circle. So where is my theta? It's from 0 to pi over 2. So as you see, after I do this vector field integration over this line, first I use the Green theory, change it to a normal one, then I use the polar coordinates. I do a polar coordinates, make my integration way easier. All right, so now in here, this will just be the theta so it will be just the theta 0 pi over 2. Then r cube will be r fourth to the r4 0 over 5, right? So now here it will be, what here is 625. So the total work have been done is 625 over 8 of the pi here. That will be the integrations for, this line integrals here. All right, so the purpose for this video, want to make sure the number, so the first problem we did here, be very careful. If your curve is not a positive orientation, then make sure you need to switch it, right? So when you switch it, make sure you put a negative sign in the front. So the negative C right now, because C is negative orientation. So negative C will be the positive orientation, right? Because the C is clockwise. So the negative sign become negative counterclockwise. So it will be a positive orientation, which satisfies the Green's series here. Okay, that's it. And I think after we did so many 5 problems total, I hope you get a very good understanding about what is a green theory try to do and how to use it if very effectively. All right, that's it. Okay, so we'll work on the next topics. Okay, bye.